Today we're going to be talking about binary numbers. But before we get into binary, let's start with something we're a little bit more familiar with, decimal numbers. And we're going to see why it is so important to count from 0. So here are the digits we're familiar with. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So those are the digits we're familiar with. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But those are 10 digits. We know 0 to 9, which is 10 digits, and this is called base 10. It's called base 10 because, well, there's 10 digits. I know you know this, but let's look at the weight of each column. And this is just to kind of get in the right mindset, kind of work with something you're familiar with, and kind of see how this works. All right, so we know we have a ones place, tens place, hundreds, thousands, etc. So let's write that out. So we have a ones place. I'm going to write this in reverse, so it's actually what the number looks like. A ones place is going to be 10 to the 0, because remember we start counting at 0, so that's actually the 0 spot. And then in the tens place, 10 to the 1, and the hundreds place, 10 squared, in the thousands place, 10 cubed, 10,000s place, 10 to the 4th, and it just kind of goes on from there. Kind of get the gist. All right, so let's do the math of this. So if it's 10 to the 0, that is just going to be 1. It's the ones place. 10 to the 1 is 10. That's the tens place. 10 squared, hundreds, the hundreds place, 10 cubed, 1,000, 10 to the 4th, 10,000, and of course, once again, I think we all see where this is going. 10 to the 6 is, whoa, barely squeeze that in there, 1 million. All right, and now let's count the position. And again, we're going to count from 0. 0, 1, 2, 3, 4, 5, 6. The position of the digit is the exponent. That is crucial. And again, we always start counting from 0 whenever we're doing anything with computers. All right, let's see this idea broken down with a real number. Let's use the number 9,742. We have 2 is in the ones place, 4 is in the tens place, 7 is in the hundreds, and 9 is in the thousands, right? And let's label the positions. Position 0, 1, 2, and 3. 0, 1, 2, 3. Good. All right, so we have 9 times 10, because we're base 10, and we have a 3 over here, so that 3 will be the exponent of the 10, plus 7 times 10 squared. Let's see where that 2 came from. Plus 4 times 10 to the power of 1, plus 2 times 10 to the power of 0. All right, so that's 9 times 1,000. 9,000 plus 7, that is a 7 by the way. 7 times 10 squared, that's going to be 700, plus 4 times 10 to the 1, 4 times 10 is 40, plus 2 times 10 to the 0, 10 to the 0 is 1, times 2 is just that, 2. Of course, 9,000 plus 700 plus 40 plus 2 is 9,742. Seems straightforward, seems like why you're learning this, but again, this is for the sake of becoming familiar with what we're about to be doing, which is working with binary. Okay, so something important here. An n-digit decimal number has 10 to the n possibilities. I'm going to write that out. So an n-digit decimal number has 10 to the n possibilities. I recommend taking that as a note. This is going to be really important for later on, especially as you get further into these classes. So what exactly does this mean? This means a 2-digit number in base 10 has 10 squared possibilities, which equals 100. That's 100 possibilities. But what's the actual range? Because it doesn't go to 100. Because remember, we always start at 0. So we're going to do range is going to be 10 to the n minus 1. So 10 squared minus 1 equals 99. So the range of a 2-digit number is 0 to 99 if we're talking about base 10. Which makes sense. What's the largest 2-digit number you can think of in our normal number system? It's of course 99. And then if it's a 3-digit number, it's 999. 4-digit number would be 9,999. So again, this is all stuff that you should be familiar with, and we're going over this just to get ready to kind of translate this into something we're not so familiar with, which is going to be the binary. So let's take that background of base 10, which is called decimal, stuff that you already know, stuff that we're used to, and we're going to apply it to binary. There are only 2 digits, 0 or 1. Binary, right? 2 options, 0 or 1. And this, because there's only 2 options, and you guessed to what base this is going to be, if you guessed base 10, then you would be wrong. That's what we normally use. This is base 2, because there's 2 options. And an n-bit binary number has 2 to the n possibilities. Remember, this is your base 2. N is the number of digits, and that's how many possibilities there are. So if there's only 1 digit, 2 to the 1 equals 2. That's true. There's only 2 possibilities, right? It's got to be a 0 or a 1. And also remember, each column is a bit. So if we have 1, 0, 1, 0, that's a bit, that's a bit, that's a bit, that's a bit. This is a 4-bit. It's a 4-bit binary number. So here's the interesting question. What would be the range of a 4-bit number? If we're working with binary, we have a base of 2. Right? So what's n going to be? N, again, is going to be number of digits. So n here is going to equal 4. Because we're working with 4 bits. So 2 to the 4, and 2 to the 4th, of course, is 16. So there's 16 possibilities. 0, 0, 0, 0, all the way up through 1, 1, 1, 1. Of course, 0, 0, 0, 0 equals 0. 1, 1, 1, 1 equals, any guesses? 15. Because it's always going to be 2 to the n minus 1 equals your range. So your range is still 2 to the n minus 1, so 2 to the 4th minus 1 equals 16 minus 1 equals 15. Range is 0 to 15 in decimal. And there you go. Really, not that much to it. So now, let's get into some thicker weeds. It's about converting binary to decimal. Just like base 10 had 10 raised to the power of the column of the digit we're referring to, base 2 is 2 raised to the power of that bit. Something I really, really implore you to do is start memorizing your powers of 2s. Okay, so what I have here is a pretty important list of numbers. So these are your places, 0, 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and you kind of see where this goes, all the way down to the 8th being 256. I implore you to have that memorized. That is going to be incredibly crucial. Later we're going to be talking about basically like your first 15 values of binary, which is 4-bit, anywhere 0 through 15. I really recommend getting to where you can look at any 4-bit binary number and being able to rapidly convert it to decimal form. That's going to help you out a whole lot later on. But for now, let's just focus on doing some simple conversions. All right, so let's convert 1111 to decimal. All right, so we have 1111. Just make it formal. We're in base 2, which means it's binary. So let's convert that to decimal. First thing we want to do is, I like working right to left. So we're going to have 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed. All right, so now that we have everything set up, and I hope you see where this came from. We're in digit number 0, because 0, 1, 2, 3, that's what spotted is, that's the column. We have number 1, that's 1 times 2, because we're using base 2, binary, to the power of 0. Column number 1, 1 times 2 to the power of 1. Column number 2 is a 1, so it's 1 times 2 squared. Column number 3, again, that 3 is the exponent, 1 times 2 cubed. All right, so what's 2 cubed? That's 8, so it's 1 times 8 is 8 plus. What's 2 squared? That's 4. 1 times 4 is 4 plus. 2 to the 1 is 2. 1 times 2 is 2, and then plus, remember 2 to the 0 is 1. 1 times 1 is 1. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15 in decimal or base 10. And there you have it. That's your first example. Now let's convert decimal to binary. For converting decimal to binary, what you're going to do is you're going to find the largest power of 2 smaller than whatever your decimal number is. You're going to subtract it, and then you're going to repeat that process down to 0. All right, so here we go. Let's use 84 base 10. 84, it's decimal, so it's base 10. Okay, so first let's write out 84. Now, what is the largest power of 2 that's smaller than 84? That would be 64. You have 0, 1, 2, 4, 8, 16, 32, 64, 128. 128 is too big, so 64. 84 minus 64 equals 20. Okay, so 64 is important. So now we have 20 minus the power of 2. Largest power of 2 that's smaller than 20 is 16. That equals 4. And then largest power of 4, I shouldn't say less than, say less than or equal to. 4 minus 4 equals 0. So the 64 and the 16 are important. So you're going to have 3 digits in your binary number that are a value of 1. In other words, they're on. All right, so this is where knowing these power of 2s and where they're going to fall in line on this table here is really crucial. And test tip, write this out, this table down here, 0, 1, 2, 3, 4, 5, 6, 7, 8, those are going to be your powers of 2s. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, etc., down to at least 2 to the 8th being 256. You really, really, really need to know that. Okay, so 4, 16, and 64. Those are your powers of 2. All right, so let's start at the right of the numbers down there at the bottom. 2 to the 0 is 1. Nope, so that's off. Do we have a 2, which is the 1 spot? Nope, that's off. Now we have a 4, that's 2 squared, so yep, that's on. We have an 8, nope. Do we have a 16? Yes, on. Do we have a 32? Nope. Do we have a 64? Yes, on. And there you go. 1, 0, 1, 0, 1, 0, 0 equals 84. And there you have it.